Okay, cool. So in machine learning, the only thing I want to conceptually show with these slides is that yes, ML is basically the entire deal about like taking your data and then like iterating over that data to find closer and closer solutions. And well, deep learning is a huge part of that because the way ML is classified is you have three main approaches, right? In every approach, you're starting with like a big chunk of data, right? But there's different ways with about that you can go processing them, mainly depending on whether your data is labels. Is it drawing anything? Okay, cool. Yeah. Okay, this is being quite problematic. Much worse than OneNote. Okay, whatever. I'm not gonna bother with this. I'll go directly to OneNote when I need to. But you have some sort of data. Whenever your data and their features are explicitly specified, which means like your data is labeled as either a cat or a dog, then you don't need to have too many layers in your model which are going to dedicate their time over searching for these labels. When these labels are already given, you have two things that you can do with these labels. Either you have two different categories of data over here and you want to do you say you want to put you want to classify these two things into their separate categories accurately based on whichever datas are most like structurally similar and what is structurally similar to this. So there's either one way about classifying it, or you can take the exact same data set and you can try to apply regression. Regression means that you're trying to find the trend in your data. So suppose suppose you're modeling like muscle mass versus steroids, right? You're not going to get a clean graph where okay, someone has a continuous amount of increasing dosage of steroids and their muscle mass is also continuously increasing. You're going to have repeated trials. You're going to randomly sample their muscle mass and check with their steroid levels, and when you graph it all out, it's going to be noisy, right? But since you and I like commonly know that steroids do have that effect, we can see that although these points are random, although they're not like clean and continuous, you can draw a line that approximates their trend. That gives you a rough idea about the rate at which the steroid is being effective. Now, in unsupervised learning, you have the same thing about classification. In this, it's called clustering. The only thing is, in unsupervised learning, since your labels are not given, in this thing, it's much clearer to tell because all of these data have their individual labels. The only, what do you say? The only thing that the model has to do is classify it based on said labels directly. But this has to actually study and process the objects themselves and then determine different trends or different labels that can separate these things. Okay. And reinforcement learning, you have basically your model or agent, which performs some action and you punish or reward it based on whether it's doing the right thing or not. So you perform an action, it goes into that environment, it evaluates if it's the right action or not, sends back a feedback. This feedback is either a punishment or a reward, and that changes the state of your agent for the next iteration. Okay. So deep learning almost entirely lives in this unsupervised learning thing. But the reason why deep learning is such a huge chunk about machine learning is because with the magnitude of data that we have now, the most important and the most useful information does not come for free within its labels. So almost everything benefits from extra study or a more deeper feature extraction. What I mean by feature extraction is looking at a bunch of data and deciding what differentiates two pieces of data. So in the case of labels, your labels are doing the work of differentiating two pieces of data. You have two pieces of data, you look at their respective labels and you compare them. In the case of clustering, not in the case of clustering, in the case of deep learning, you have a bunch of extra layers inside your model, and they're almost entirely dedicated to figuring out what those features are so that it can best classify and determine the differences between two objects. So yeah, okay, cool. So in a typical ML model, you first train it based on test data where the labels are clearly given over here, and you obtain your weights and all the reset training happens and finishes, and then you take your label data over here, labeled hexagon, square, triangle, etc., circle, so on, and that is chucked into the thing, and then it's supposed to look at those objects based on its training time. It's going to either classify into a hexagon or triangle. In unsupervised learning, the same thing. You're just not telling it what shape it has, right? And reinforcement learning, the same thing. Your agent is over here. It has so and so environment. It performs some action within this entire environment. If it goes towards the fire, it reduces its points, and there's a penalty. If it goes towards the water, it's rewarded. Very simple stuff. So broadly, you're going to see these as the three main fields in ML. The thing about supervised learning is it's used in the case where your features are known, and you in the field of supervised learning, it's often not enough to just go into classification and regression alone. It's more dependent on like over here the entire what do you say the entire thing that you care most about is the accuracy of your classification. In clustering, we care more about the features that you extract, and in reinforcement learning, we care more about honing your agent's behavior into a certain desired uh, behavior. So obviously, these are not clean-cut boundaries between ML. These often have a lot of what do you say overlap. There's not going to be overlap between supervised and unsupervised. These are polar opposites, but there's going to be overlap between supervised reinforcement learning and unsupervised reinforcement learning. So in deep learning, we won't. Yeah, okay. Hmm. So difference between machine learning and deep learning. In deep learning, you're trained on raw images. In ML, what do you say? You're given the different features that you can detect through your thing. These features are then chucked into a support vector machine. A support vector machine is, you can think of it as this black box which takes um, some object and spits out representations of it in forms of vectors. So if you had pictures of dogs, then it would what do you say? It would throw out pictures of it would throw out a vector that similarly represents a dog. Now suppose we're talking about a text model, right? Let me see if I can draw this because I don't think it'll. Yeah, cool. So you have a dog. Oh, thank God, it's working. Okay. You have an SVM over here. It spits out a dog vector. Okay, something like this. Now, say you had, what do you say, you're chucking some text through a support vector machine. And suppose that text just happened to be do. Okay, spits out some vector. This is a do vector. All is fine. Similarly,
Um,
go on.
I think you're lagging a bit.
Yeah,
How bad am I lagging? How long have I been lagging?
horrible.
Horrible.
Yeah, it's horrible.
Past two
Come on,
minutes, 1 minute.
relax.
Give or take. Yeah.
Yeah.
I'm gonna have to close a bunch of tabs.
If you're off your camera,
Yeah,
maybe.
I could.
Maybe try closing some of those
Yeah,
tabs.
bro, I have to go through all of
Yeah.
them, dude. I have to go through all of them. These are like
uh, Brave only, no.
brave only. But see, I am
Holy
I
shit.
completely depend on pressurizing myself to get anything done. So if I see an overwhelming amount of things to do, it's the only way I'll get anything done. If I have
Right,
if I
right,
have
right.
things one by one or hidden away, I'll be like, light le lo yaar, kuch bhi nahi hoga. Okay, how is it now?
Makes sense,
How
makes
is it now?
sense. Fine, fine. It's okay, it's better, it's
Got
better,
it.
it's better, yeah.
Yeah.
Okay, phew. So how? What was the last thing you guys remember hearing clearly?
ML and DL, you were explaining that
This much.
much.
Okay, so by the time
We
I
were on
got
that
here, you
page only.
guys were clear
From
already.
there on.
Yeah.
Yeah, you told support vector machine and all, you explained, we understood
So
after
the
that.
do and undo example is like somewhat clear, right? I'm about to explain undo. Yeah,
Yeah,
so all I
yeah,
mean to express again is like, now we have undo. Undo is the opposite of do. So it's going to be the negative direction. You can think of it as though it's -2. Okay. So this is what we mean by having some sort of vector representation. Wow, my drawing is also better now. Okay, not surprising. But yeah, okay. So this is what we mean by having some sort of vector representation. And in the case of a regular ML thing, what you have is these, you say, let's forget about color histograms for now. Let's just talk about shapes and text patterns. You have these shapes and text patterns, you chuck it into an SVM, it gives you a bunch of vectors. And those vectors, like, they have this nice structure around them, such that, like, opposite things are pointed in opposite directions and yada yada. So you know what two words are similar based on just these vectors. So you know that undo and do are basically the opposite just by looking at these vectors without knowing any actual English. And the thing is, over here you had some actual text patterns and shapes to look at, whereas in typical DL approach, you have to first find these edges. You have to find these features, and only then you can chug it into an SVM and do the normal ML stuff. So the other thing about this is it's not necessarily always going to detect these, like, nice patterns right out of the box. It's going to first, do you say, detect the edges of the thing. Let's suppose we're talking about triangles, right? So if I had a set of purely triangles and I had some neural network down here with like so and so layers going down, and it's going to give me like one of either like a square or a triangle or a circle. Wow, that's a terrible circle. Okay, cool. So let's suppose it gives this, right? So the first thing I'm going to do is I'm going to take this triangle, I'm going to convert it into some sort of vector representation. And then once I have that vector representation, I can chuck it into a neural network, which will do all sorts of complicated linear functions on them, operations on them. And as it passes through these layers, the first layer over here is simply input. So it's just going to take this vector representation, pass it on to the next. The next layer is going to detect something super basic. So it's going to, suppose we have all these different shapes, right? So the most basic thing you can probably guess that this layer might look at is, okay, maybe it's just counting the number of vertices in each of these shapes, right? So the first layer is just going to look at the points in this thing. The next layer is going to look at pairs of these points, which is what an edge is. So in the next layer, you're going to go up a layer of abstraction and you're going to look at a larger feature. So you're going to look at how smaller features build up and make bigger features. And so as you add more layers, you're seeing how these different features accumulate and form more larger, bigger patterns. And in the end, the largest pattern of them all, since, like, in second layer already you have an edge and your, what do you say, shapes are defined by their edges alone, you don't need any further layer than that. Immediately you can jump into classification. So it's going to give you a set of three numbers over here. The highest number is going to be the one that it's selected. So in the case where we had a triangle, over here it's going to go as input. Over here it's going to detect the number of edges over here, and it's going to find that, okay, this thing has three edges. Then it's going to go over here, it's going to be like, okay, between these three edges there's three sides only. And it's going to be like, okay, the highest chance that it has is that it's a triangle. And that triangle goes through a nonlinear function or something or the other. Think of it as a black box, and that chucks out your triangle as your answer. Okay. The main thing I wanted you to understand is that the first step in any ML workflow or any say model is that you take your features and you convert it into a vector. Okay, that's the first thing, the most important thing to understand, because depending on your representation of your data, the better your representation, the better your model. Okay, now I will just go ahead to a diagram of a neural model. Okay, cool. So let's suppose this is our what do you say neural network, the whole thing. Let's just for just for the sake of simplicity, let's assume this is the entire neural network. So we have three things to focus on. We have our input over here, which is x1, x2, x3. We have the weights that are associated with this input. We then have this random expression over here, which currently makes no sense to us. Another random function over here, which is undefined, and it gives us some certain output. Okay, and so let's recall what we saw in the previous thing. We saw that, okay, we had some data over here, we chucked it into an SVM, and we got some vector. And this x1, x2, x3 is that vector. Okay, so first layer is just taking the input. Second layer is going to be initialized with some random weights. These random weights are like, what do you say, just arbitrary numbers that are going to adapt to your data such that it represents your features. So when your layer in between detects something, it's basically changing these weights to better differentiate between your labels or your features. Okay, now these weights are going to, what do you say, these are going to transform your input thing. So x is your input vector, your weight vector or weight matrix is what do you say, wt, and then along with t you're going to add some bias. So now, since we understood these two parts over here, right, out of 1 2 3 4 5, you understand 2 out of 5 things now. So let's go and understand why this looks like this. Okay, so now I'm going to go back and I'm going to look at why it's called a neural network, neurons and stuff like that. So if you take a look at a typical neuron, you see these dendrites, which is going to connect to all the other neurons over here. Okay, and the cell body is basically the thing that's performing your computation. Your axon over here is the one that's going to pass your output, and your synapses over here is going to pass it to other neural networks like this. Okay, so what's basically happening is your dendrites is acting like your first layer, where it takes the input as is, and what you'll see is that with do you say, what you'll notice when you're studying neurons, or what they notice at least when they were studying neurons, is that sure, these neurons conduct electricity and that's how the brain functions, but these neurons are basically responding to some stimulus, right? Like for example, you hear a voice, you hear a voice that you recognize, you hear a voice that you don't recognize. In one case, you have higher neuron activation where you're like, oh shit, I know who that is, and your brain's going to be like, oh, that is someone I know, right? In the other case, you don't know who it is, your brain's probably going to ignore it. So what is this? Is basically a threshold, right? A threshold where, on the basis of whether you recognize someone, you're either going to, like, your neurons are going to activate or they're not going to activate. So this is where the thing about bias comes from. So if you recognize the person, you're a bunch of these neurons are going to light up. The signal that's coming into this neuron is going to be way stronger. So this neuron will be like, oh shit, I know this guy. It's going to go over here. It's going to give a stronger signal too. In the case where it's not going to recognize who it is, maybe this one is not going to activate, maybe this one is not going to activate. Suppose only this neuron is going to activate. It's going to give an extremely weak signal, which is not worth transmitting all the way to the next neuron. So this cell body, this neuron is just going to ignore this, what do you say, this signal because it's lesser than the bias. So the same thing. Now we're going to go back over here and look at this, right? So the weights over here are what already exists in what is already unique to each cell body. What is like the transformation that's happening within the cell body. Now, what decides whether this signal goes beyond the cell body onto the axon and every other neuron that this thing is connected to is what this bias term is. So, depending on whether it increases this bias, it's going to go up or down. Now, let's talk about what sigmoid is. Okay, sigma or sigmoid, I'm confusing that a bit. So, sigma is some arbitrary function that acts as a non-linear activation function. Now, let's explain what this means, right? So, what sigmoid does is, suppose sigma is something like the step function, right? So, sigma is equal to floor of x. Okay, or let's just say, what's that? S, yeah, sgn of x, right? So if you're plotting x and sgn across x, then in the case where it is less than 1, it's going to be what do you say, it's going to be 0. In the case where it finally hits 1, it's going to pop up to 1, and everything after that is going to be 1. So what this means is, if this entire computation is still something positive or greater than 1, then it's going to actually activate your neuron and it's going to pass along its output. In the case where whatever your output is lesser than 0, which means it's not actually enough to activate the threshold, then it's just going to get ignored over here. Okay? Mm, everything cool so far? Does anyone have any doubts?
No.
Can you explain bias again?
Bias. Okay. So bias is basically your threshold that, what do you say, that ignores anything that is a, what do you say, a weaker signal, right? So in this case, bias is some arbitrary number that you assign to each neuron in neural network, and on the basis of your bias, it's going to either what do you say, output a 0 or a 1 per neuron. So in the case where,
So it's like giving us binary
yeah,
only.
in this case it's binary. Since it's a simple step function, it's only going to give you a binary output.
Right, right, right.
Cool.
Okay, okay, perfect. Thank you.
mm, for now we can stop here, and we will now go to the other thing. So this, I went through this PDF just to give a conceptual overview about everything. Now in this thing we will go through what, let's see if I have an annotate function feature over here on Brave. Guys, don't download Brave. Brave is terrible. I hate every second of this thing. I would rather use Microsoft Edge. Okay, so now we're going to talk about tensors. What are tensors? So I'm going to go back to this PDF because it's the only free space I have. Okay, cool. So what are tensors? Back when bachpan mein, when we were talking about arrays and stuff, we talked about arrays like, okay, you can have some array of one-dimensional numbers, right? Let's say 2, 3, and so on, right? What are arrays in the end? They're basically just a list of numbers of some sort. right? Now, do you say when we were talking about arrays, you'd go and you'd define an array simply like this. This will define some n-dimensional vector, and you just fill in all these values with like a for loop or something, right? So you'd have one for loop, you'd tediously go through every single element over here, fill in all of this manually, right? Similarly, if you wanted a matrix, what would you do? You would just simply write another square brackets. You'd say int array square 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 square. I'm saying nn or nm, and now you have two for loops. Now I don't know if I should switch to OneNote because the writing on these PDFs is so garbage, and you'd fill in all the values of your array one by one. Okay, easy now. Now let's think about this slightly differently. Instead of having single values in over here, right, you can consider this matrix as if it was a 1D array where your entries are arrays on their own. So over here I have one vector, over here I have another vector, over here I have another vector, and so on, right? Making sense so far? I can simply construct a matrix like this. Easy, na? Guys?
Yes,
Yeah.
yes.
Yeah.
So
Yes.
now
Yes. Yes.
syntax wise, you can see a hint of this coming, where in any typical syntax, you have some data type over here, and you put in square brackets like this. It means that you have a list of this data type. Doesn't matter what that data type is. So when you say array of n, array like int over here, let's say, sorry, my bad. When I say int like this, I have integers over here. When I say int of two things like this, you can think of it as I'm having a list of int n's like this. Okay, peace now. So like this is where tensors come in. Tensors are easy. All you have to do is you have to think of it like, oh, what I'm doing is instead of having what do you say, matrices and vectors, I'm just generalizing it so that I can have arbitrary number of rows and columns and so forth and so on. So basically all I'm doing is I'm having a list of the previous data type. So I have a list of these things. That's going to be an array containing all these three things. I don't have that much patience with my drawing tab to draw that. But yeah, you can just imagine this specific term printed out three times like this. And now to define this specific term, you're going to go back one layer, and each of those specific terms is again going to be a list containing this specific term. And you keep going down and down until you get something that's primitive and small that you can represent as a single number like this, a scalar if you will. Okay, make sense?
Could you explain it
Okay,
again?
think about it this way. Okay, I'll start from the top. So I'll talk about it in terms of generalizing it further. So you have like a scalar. What are scalars? There are basically zero dimensional, where you have just some random number in there. What is a vector? This thing is one dimensional in the case where you have a list like 1 2 3 like this. What is a matrix? This is two dimensional and it looks like a little square. Now what is a rank 3 tensor, or just simply a 3 tensor? A 3 tensor is going to have something that looks like this. So inside each of these, I'm going to have 1, 2, 3, 4 SR. I'm going to fill the entire thing. A 4 tensor is a 4-dimensional thing. So I can't draw it on a 2D screen, which is projecting a 3D object. So on and on it goes, is just higher and higher dimension. So in the first example, what I was trying to explain it through is by using recursive data types, where you have this whole deal about having a data type and some square brackets, and so you delineate, you push it down by talking about a list of whatever's on the left side of this thing. So this is why this explanation might have been confusing if you weren't looking at it from a recursive point of view. But if you want to look at it from a geometric point of view, you can just think of it as always one-upping your number of dimensions. Does this explanation make more sense?
Yeah.
Okay, cool. Now one extra
Yeah.
thing about a tensor is we already have arrays and matrices, right? And we use these words interchangeably, but when we talk about a matrix, we're like, okay, sure, it has to be this square little rectangle that has its fancy little values, right? And we're like, okay, an array allows me to add as many dimensions I want. Why should I bother calling it an array instead of why should I bother calling it a tensor instead of sticking to my usual term of arrays? So one pretty important thing about matrix that allows a lot of linear algebra is the matrix multiplication, right? You have one matrix over here, you have another matrix over here. It's not a simple product of just element-wise multiplying these things. You have that random this and this thing where you multiply these two, and you do all that random things that look like they come out of nowhere, right? So over here in matrix, you have your matrix multiplication, and in tensors, you have your similar tensor multiplication. So this multiplication is key to keeping that sort of nice structure, allowing you to multiply and do all sorts of linear transformations while having as many dimensions as you want. So you're not restricted to just having this boring old square. Okay. So let me just summarize the things that I do want you to take away from. So whichever way you understood what I mean by tensors, there's two things I want you to understand. I want you to understand this structure, this like increasing in dimension sort of deal, where you start with 0 dimensions, 1 dimensions, 2 dimensions, and 3 dimensions, and any n dimensions that you want. Are most people clear with this part? Cool.
Yeah. So 3D sensor is like an representation of image, right?
So I'll talk about the images thing right after I clear this part. So over here, the next thing I want to confirm is, does everyone understand why we bother calling it a tensor instead of just an n-dimensional array? All I want you to take away is that this added structure of a product is there. That's it. Matrix product, matrix multiplication, that stuff is well defined. That's all. So now if everyone's clear with that, I'll talk about how your images can be represented as a three-dimensional tensor. Is everyone clear? Cool.
Yes.
Yes.
So let's see, maybe by luck. Okay, no, wait. Actually, I remember it being there in the other website. This will be clearer because I don't feel confident to use colors. Okay, so your image is, what do you say? This is your raw image, and let's say it's 224 pixels by 224 pixels. This is the example that's simply given, right? Now, within your actual image, over here, when we talk about tensors, instead of saying the word dimensions, we say the word shape. Okay, and what shape basically means is, okay, how many rows, how many columns, how many width, all that stuff. Okay, so the shape is only telling you the dimensions of your image. So you'll see 2 over here, you'll see 2 over here, you'll be like, okay, that's the same as the image that's given over here. You'll probably wonder what this 3 means. The 3 only means that your image is represented in RGB format. So instead of having like some you say arbitrary value in this thing, it's going to be a sum of a specific red value, a specific green value, and a specific blue value. So every single pixel actually has three different values of its own. So you need to account for those three values as well. And that is going to like faithfully represent what your image is actually looking like. Okay. So which is why if you take your image like this, you're going to have to pre-process it so that it's like, in this format where you actually have real values for each of these, by which I mean, like, you have some value for red, some value for green, some value for blue, along with its pixel values. And then that will give you your actual tensor representation. So think of it as this way, okay? You had raw data. Think of an SVM as this little this little part in the middle, and it chucks out your vector representation or tensor representation of your data. Is that clear? Okay.
Yeah.
Yes.
So this is a 3D, no?
This is 3D.
Like 3D sense.
This is 3D,
Tensor.
yes. Okay, cool. So now we're going to go into some PyTorch syntax. So now that we understand what tensors are, we're going to find out that, like, tensors are basically everywhere. So cool. So over here we can look through this part later, and we're going to look at the things that I explained just in the syntax of tensor. So now what I want everyone to focus on is just to understand that syntax. Just pay attention to how these things are defined, how these things are initialized, and try to relate them to the things I already explained. Okay. So what I already explained was, yes, this is a zero-dimensional tensor. A scalar is a single number, which is a zero-dimensional tensor. Fine. How do we define this? So over here is scalar. We're going to call the torch.tensor function. And I'll tell you what torch is. So torch is a library where you're going to do all your deep learning stuff in. You can, oh, there's no explanation about the import thing. Okay, so oh yeah, there it is. Fine. So when you're importing PyTorch in your library, you simply type import torch. I'll have you guys run this on Colab, so don't stress too much. All I want to point out is that torch is the name of your library. So any function you call is going to be torch.something. Over here, you can see torch.version. When we went down to tensor, you saw that there was torch.tensor and so on. Okay. So your scalar, you're defining it as you're calling the torch function that will initialize a tensor with simply the value 7. So I haven't put 7 in any array over here, so it's going to return the same, what do you say, value 7. Now I want you to notice that over here, you had the value 7 over here, which is like an integer, right? But when you asked for the data type, or you asked it to return the value of scalar, it wrapped it in this data type called a tensor. So over here, you see that even though a scalar is a single number, its type is of torch tensor. All that means is now your value is wrapped within this tensor, what do you say, this tensor data type. So we can convert this tensor data type back into our Python integer. We simply take the tensor over here that we defined like this, and we can call any one of its PyTorch functions. So we can call endim over here, which will chuck out what the dimension of your tensor is. Or you can type dot item over here, and it will remove the tensor data type things that's related over there, and it'll give you the original, what do you say, data type. So in this case, you had an item over here. You chuck in, what do you say, dot item on the outside. It's going to give you back the integer. When we're going through the, it's not here, right? Okay, cool. When we're going through the Colab thing, we'll see what happens when you do a tensor data type for a vector and then you do dot item on that. You'll simply get the inside of this thing. Okay. So similarly, defining a vector is just as easy. Over here, it's almost the exact same thing that you guys have seen with your arrays. The only thing is you see this extra torch.tensor over here. And although right now it seems like it's basically unnecessary, everything that you can do with PyTorch comes with the other functions. So this is like, basically like the hello world of PyTorch. This is nothing like crazy or big. It only takes a little getting used to. So you have your typical vector that you would write like this, and you just write a torch.tensor over here. you check its dimension, it will give you a 1, and you ask for its shape. Remember, the shape is the only thing, the thing that I said about the shape is that it's going to give you the, do you say, the actual dimensions of this thing. So what I mean by that is, when you guys asked about, like, that the fact that an image is a 3D thing, over here, this will give you, if I had an image over here and I had image.endim, that is going to return 3. Now, if I had an image over here and I wrote image.shape, it's going to give you that, what do you say, the dimensions of the actual image that I told you. So 3 into 2 to 4 into 2 to 4 is going to be what it's inputting back. Only thing is, it's going to input it back as size of this thing. So again, just this outside thing is something you have to get used to. But over here, it's basically like 2 into 1 or 1 into 2, giving you the dimension of your vector. Okay. Now, same thing over here in matrix. You can see this thing is clearly 2D. So if I do endim over here, it's going to give you 2. Now, you can see that this 2D object is a 2 by 2 matrix. So when I type in shape, it's going to give 2 comma 2 with that outside torch or size thing. Okay. So again, torch.tensor, in this case, you'll notice that there's something a little bit different going on over here. This over here is a list of list of lists. So first I have this thing that looks almost exactly the same as a vector, right? Not a vector. This looks exactly the same as a matrix. But you'll see these extra square brackets outside over here, and that's what promotes this thing into a three-dimensional tensor. So the number of square brackets that you see before you get into the actual data is the dimensions of your tensor. So let's go back and look at this sort of trick back at the other like examples. So over here, we all agree that this matrix is a two-dimensional thing. We count the number of square brackets, we see 2 square brackets. Fine. Similarly, a vector is a one-dimensional thing. We go back, we count the number of square brackets, we have 1. We go to a scalar, we count the number of dimensions of a scalar, there is 0 square brackets over here. Okay. Peace, na? It's all easy only, right? Okay.
Yeah.
So now that we understand well what a tensor is, okay, so look. So this is the same example. Just look at it for 5 seconds. When you're ready to move on, I'll just go down further. I'll move ahead.
So this example is two-dimensional tensor.
So this
The
one.
one on this.
So
Yeah,
here
yeah.
it's a three-dimensional tensor. Okay.
Okay.
So this is a vector, one-dimensional thing. Matrix, one-dimensional thing. You can look at it as though this is a matrix over here. See, instead of 7 over here, I replace this vector. Instead of 10 over here, I replace this vector, and so on. Okay. Now I have a matrix where if I had a matrix where all the individual entries are a scalar, then this thing is a 2D object, right? Because 2 plus 0 gives you 2. Fine. You're adding the dimensions as you go along. In this case, you have a matrix over here. Instead, if your entries are vectors, then 2 plus 1 gives you a 3D object. Does that make sense? Cool.
Yeah.
Okay. Now, random tensors, suppose you wanted a large number of tensors, like a large dimensional tensor, and you wanted to just quickly fill in the values. So say you wanted to fill in a 7 by 7 tensor. Nobody's going to sit and painfully write down all, 49 values of your matrix. So you can just say, okay, rand, what do you say, torch.rand. That will define a random tensor. So let's look at the syntax a little more carefully. So you have some tensor name over here. You're defining it as torch.rand. Torch.rand is going to define a tensor of a certain size over here filled with random values. So the size is what you have to define. The size is similar to the shape thing that you saw way over here. See, size over here, shape over here. Basically the same thing. So you input what do you say? You input the size of your thing, 3 rows, 4 columns, and over here you're just calling the tensor. So when you call the tensor, it's going to print it with the tensor data type along with its contained values. And if you ask for the data type over here, all you have to do is you have to take the tensor name, which is a random tensor over here, dot d type, and it's going to check out the data type of your object. Now, one not important but interesting thing to note is that, like, your torch.ran thing is going to check out float values, right? What is there? Okay, now suppose you wanted a random image. You have a height column, you have a width column, you have a color column, you have height, width over here, and the number 3 is going to represent your RGB values. So if you wanted to create a random image, you're going to just take your image name, and then you're going to put torch.rand, and you're going to input its size. Okay. Now, zeros and ones. Yeah, you can, instead of, if you don't want to necessarily put in random values and you just want to initialize it to 0, then you do the exact same thing. Over here, the exact same syntax. You have torch dot zeros, and then you have your size thing mentioned over here. Okay. Again, you'll notice it's float. Okay. Similarly, you have ones, exact same thing again, torch dot ones. So you can do 3 things with your tensors. You can either fill it with random values, you can fill it with complete zeros, or you can fill it with complete ones. Okay. Now, instead, I mean, like, zeros and ones are like very basic patterns and not very useful if you wanted to print out a tensor with like numbers from 0 to 1, 1 to 100, and so 0 to 1. Sorry, my bad. I meant 1 to 10, 10 to 100, and so on. So over here, similar to Python's whole deal with range and stuff, you can you can define a start, you can define an end, and you can define a step, and it will go ahead and fill in those values for you. Over here, the range function is depreciated, which is why what depreciated means is, like, Python libraries are maintained by people, right? And so when Python or the library itself update, then certain definitions may just completely get deleted from the newer versions, or certain definitions may be changed to more modified versions. So that's what it means when it's depreciated, when, like, it no longer exists in the Python, or if it's, like, like it says over here, if it's inconsistent with its current functions, then you're going to see the word depreciate. So you're going to see this a lot if you're, like, in open software, if you're using a lot of GitHub libraries and stuff. So cool. Most of the things are done. I was hoping to go through this a little faster, but I am falling behind. Okay, tensor data types, you can define it as anything. Everything is basically tensor dot something. So over here, let's go over here. Tensor dot float 32 is going to define a tensor with is going to talk about data types where a tensor has float 32 values, tensor has float values, or so on. Does anyone have a question? No? Okay, cool. Okay. So, like we talked about, all those different extensions, shape, data type, and device are different informations you can get on tensor. So dot shape, with some tensor, you're going to get the value of the shape. Like we said, see some tensor, and then dot shape. Similarly, some tensor, and then d type. Now over here, device, this thing in you say, so this device thing is more relevant if you have actual hardware to run this on. So, GPUs are naturally much better at processing tensors than CPUs are. And so, or suppose you're lucky enough to get your hands on a TPU. These are specialized processing units which are better at handling matrix multiplication than general CPUs are. So what they do is they would rather have these big matrix multiplications happen on these GPUs and TPUs, and they would leave the rest of the processing to the CPU. So what you'll see is that you'll see a lot of you'll see most of these codes telling you key if there's a what do you say, if the word CUDA is available, then it will run over there. So what is CUDA? Let's go over here. So torch.CUDA is basically your what do you say, platform for writing parallel programming, like parallel processing programs. So you have, like, suppose, okay, so let's talk about a little bit about parallelization. So let me just go back to this matrix over here. Cool. Let's suppose we are doing matrix multiplication. We have, what do you say, this matrix over here. Let's suppose we have another matrix over here. Let's look at this as though it's a matrix. Okay, so guys, when you're looking at this picture, let's kind of forget this tensor thing. I'm just reluctant to pull out my pen and tab because it's going to lag my laptop. So bear with me. Let's suppose 7401 and all this is an actual matrix, and this is also another matrix. And just for argument's sake, let's talk about like as though we're multiplying them. Okay. So the thing I want you to notice is that the computation of this term into this term and finding out this point in your what do you say, resultant matrix is independent of if you're multiplying it with this term and this term. So instead of waiting sequentially and doing first this and then this and then this and then doing this again and so on, this would be a sequential thing that would take a lot of time to process any given matrix multiplication. If this was the case, your machine learning models would be over by the time the earth died. Instead, what we do is we take this, what do you say, we take this computation and we process them separately. So we have smaller processes that what do you say, run parallelly, and CUDA is the platform by which you use, like, these matrix multiplication, and you distribute them among different cores in your GPU. Okay, so that's just a small, like, scratching very lightly the surface of what parallel programming is. If you guys are interested, there is, I literally have it open here, I think somewhere. I don't. I think I closed it today only. So there's a programming language called Bend. If you guys are interested, yeah, there you go. Yeah, so this is one programming language which is currently still in dev, so it's pretty young as a language, and yeah, it do you say, it's useful for parallel programming languages, and you guys could give this a try if you have some spare time. It's 6 o'clock now, right? So I think I will. Okay, here's what I'll do now. So since we have run out of time, it's not like we have a little time left either. I will tell you how to just what do you say, import notebooks into your library, and not into your library. I mean how to import Python notebooks into Colab. And okay, so let's see how many people know how to do that. If many people know how to do that, I'll just tell you which notebooks to download, and then you guys can leave. If not many people know that, you can stay. I'll show you how to do that, and then we can leave. So just raise your hands. Depending on the number of people, I'll tell you the Python notebooks that we need to download, and we can end it. Otherwise, I'll just show you how to do that. So raise your hands if you know how to import a library into your Colab. Okay, bro. Samarthana began. Go off, bro. Cool. I'll, what do you say? For you guys, I'll just put in the notebooks that you guys should finish, and you guys can shut up. You're saying something?
Like you can show for one
Yeah,
and we'll
yeah. I won't
download.
make you guys download both of them. I'll show you guys how to do one, and then I'll pass the other
Yeah.
two. So one has to do with geometric deep learning. The other one has to do with actual exercises.
Mm.
What I want you guys to do is over here you'll see, okay, so whenever you see a Python notebook, you'll see IPPYNB over here. So that is a Python notebook or a Jupyter notebook. These two names are used interchangeably. So you can run a lot of software by simply just do you say, importing your notebooks into Colab and then running it on that. So let's go ahead and do that for now. Okay. So cool. Okay, so let me copy maybe this link. No, not friend. Where is geometric? Yeah, there it is. Okay. So I'll just go ahead, copy this link, or maybe I'll actually just go ahead and copy the link from here. Okay, so suppose you found the repository which you want to download notebooks from, which you'll see over here in these what do you say, folders. So if you want to download a repository and run it in Google Colab, your first step is to go to the GitHub thing and you want to copy this link over here. So you're going to click on code over here. Actually, I'll send this link so you guys can follow along. In the meantime, everyone open Colab. So if you've opened Colab, just go ahead and raise your hand. When everyone is done, I will, what do you say? Oh God. When everyone has Colab open, I'll proceed. Oh, it's breaking. Oh, it was breaking. I didn't see the chat until now. Sorry, bro, again. I didn't mean to leave you on red.
It's okay, bro. Used to it.
Okay. How many are there? There are 10 people. 6 more. Oh, I hope clicking on this isn't going to make this thing lag. Okay, 6 hands. Fine. God, I need a new laptop. Okay. How many are left? Okay, fine. We'll wait for you guys to do. After everyone has their thing open, I'll just go ahead. Does everyone have it? I can't tell because it's. I thought Sharat had it open. Okay. Sharat, Samarth, Soha, and Farshad.
Bro, in the repository you just sent, there was in the README only the command was there. We just have to copy paste that and
Oh, that's for
right.
locally downloading your GitHub, no? That's if you want to use git clone. Or wait, this is a Python package, so you can just probably pip install, okay?
No.
But
Go down there. Yeah, pip install. Yeah. Just copy that and we
yeah,
can download
for
this in
this notebook,
Colab also.
these guys were nice enough to have that sort of thing ready. But some notebooks just have their Python libraries open as is,
Yeah.
right? So they don't have the, not Python, sorry. What I
Yeah.
mean to say is some libraries have their Python notebooks just lying there and they don't have this, what do you say, local install thing for each of these notebooks. So let's ignore that for now and let's just see how
Mm-hmm.
to, what do you say, open a notebook anyway. Is everyone's done? I can't tell. There are 6 raised hands and 7. Okay. When majority is done, I guess I'll continue. Is this everyone that's there? Soha. I suppose I'll continue. It's a majority.
Except
It's a majority.
Soha,
So it's
everyone
fine.
has
We
done.
don't need to vote for
Yeah.
one person. So all you're going to do is you're going to go ahead and copy the link that I sent in the chat. And when you copy that link, it's going to go ahead and open this repository. Okay. Click on this link and then copy this URL. So go to the website over here. This is why which was the main over thing. Go to this website, click on code, copy the link, and keep your hands raised if you've done that. That should take like 2 minutes, so I don't expect anyone to like take too long. Shall I proceed? Just copying a link. Cool.
Yeah.
So over here you go to file, click on open notebook, and then over here you select GitHub instead of recent, and over here you check in that link. Okay. Can everyone see it up to this part? Okay. So
Yes, yes.
this is a specific issue about this particular repository where, like, this repository says PyTorch geometric, and this one for some reason when goes to advanced PyTorch. So no matter, for now let's ignore this issue. But yeah, you want to, if you want, you can select, like, this particular person. So Antonio has like several different repositories. You can scroll, browse, and find different like repositories that you want to install from. Over here you can select the correct one over here. If you want to select a particular branch, you can do that as well. Most things are going to be in your main branch only, so you don't need to worry about that. And yeah, that's basically it. You just click on the notebook that you're interested in, and that opens it up, and you're done. Okay, was everyone able to follow that along? So I'll lower everyone's hands, raise them once again if you guys have done the following. Okay, simple, right? Easy.
Yeah.
Okay, so I'm assuming the newly raised hands are all everyone who's done it, no? If I see 7 again, then we can conclude this meeting. I will send the links that I want you guys to download in the, like, in the WhatsApp group. Out of which the PyTorch thing, I not the PyTorch thing, the PyTorch geometric thing. Let's see, does it open here? Yeah. So let's go through this notebook for about 5 minutes. So in this thing, what I was planning to do is I thought we'll explain how graph neural networks work in some degree. And in this library, you have, what do you say? You already have a pre-built implementation of a graph neural network. So if you run all of these cells individually, I'll tell you what happens. So the first thing you're going to, what do you say, import torch. These are just some random things for the environment so that you can do all the pip install stuff. Okay. And then you're going to import torch geometric. This is the next thing that we'll be covering. Hopefully I'll pick up the pace by the next lecture. But yeah, this will be the next thing we're covering. Over here, some arbitrary data set was called and downloaded. And everything that we do upon, like, everything that we pass through the graph neural network is this data set. So over here, these are just some random, what do you say, features of this data set. You're just checking, classes, features, and so on. This is just arbitrary things you could look. Now, can let me ask a question. Just anyone who can answer, just go ahead. What's the dimension of this tensor over here? If I put in ndim, yeah, 2.
Two,
Two.
This
two,
one
two,
is
two.
1, right, guys? This one is also
Yeah. Right.
2.
Right.
Correct, no?
Two.
Okay. So
Yeah.
now
Yes.
code-wise, let's look at the structure of most neural networks. So I don't want you to look at everything inside this and remember the words. Okay. What I want you to remember is structurally what it looks like. Okay. So every neural network is going to start with your class net. You're going to define some class which is going to take in some neural network module from this thing. Okay. So you have net over here. You have torch nn over here, or torch nn module. Okay. The next step immediately is you're going to, what do you say, inherit the definition of net from this neural network implementation. So this is why over here inside the initialization thing, what is this initialization thing? It's basically a constructor, right, guys? So you have a constructor over here, and it's passing itself, and it's going up to what torch nn defines its constructor as. It performs that initialization. Okay. After that construction is done, it's going to, this is something we'll look at later, because, like, that's not what I want to focus on right now. So structure wise, we understand one thing so far. We have some class net that inherits this torch nn class, and it's going to construct the class based on that parent class. And then the next thing that we're going to define is we're going to define what forward propagation is. So when we were talking about neural networks and we talked about, okay, we had like the first input layer. Let's see if I can pull up the diagram without lagging my mind away. Okay, cool. You have the input layer over here, you have your weights, all the calculation happens, goes through a reactivation thing. And the first thing you're going to do is you're going to send it forward, right? So this simple act of passing it along to the next layer is called, what do you say, uh, forward propagation. So this entire thing is one neuron, and there's a bunch of these stacked together on top, each of them passing one input like this. And each of them taking something like 4 inputs over here with 4 of their specific weights. Okay, so yeah, I was going through the structure of this thing. Yeah, so that's what forward is over here, according to, like, the structure of a what is this, graphic neural net graphic neural I mean graph neural network. You're going to define the update thing. So over here you'll see that x is updated with this random function over here, which takes in the data of x, and somehow it updates something and passes it along and reassigns that value to x. So this is basically the forward propagation that's happening. And before you forward propagate, it's going to do that activation function over here. So as you remember, that activation function is going to be something like that step function over here that squishes your what do you say, weighted sum and all your output into, in this case, either a 0 or 1. And maybe in the next lecture we'll also have a look at other what do you say, different activation functions. So this is how you'll implement pre-existing models. So over here, sage.conv is an existing model defined within PyGeometric, which is why I wanted to show you guys how to do it, because over here the training and everything, like, we're not actually implementing these neurons from scratch. We're not defining every single layer on our own. We're taking a known model and we're just, what do you say, we're making choices basically. So you'll have a train function over here, you'll have a test function over here. The inside structure we'll touch upon it later, but overall the structure of your model is like this. So class, constructor, forward propagation, training function, test function, and over here you're gonna have a for loop that goes through each, like, that computes every iteration. So structurally, is everyone clear with this thing? Okay,
Yeah.
Sort of. We'll have to look at the
probably
notes.
better. Yeah, yeah.
Yeah, yeah,
Then
yeah.
the next thing I want you guys to do is over here. There's this exercises. So these exercises should take about like 2 minutes, I think. So within this repository, you have all these, what do you say, extra exercises things that you can go ahead. So as you can see, this is also a Python notebook. So when you go to this repository, do the whole thing where you copy the link, go to Colab, open a notebook, go to GitHub, select the notebook, and you select this exercise notebook. Over here, you'll get all these blank cells over here. Okay. So you fill in these blank cells, you run them, and when you guys are done, you can compare it with the solutions. I think the solutions right here. No, yeah, this is solutions. Compare it with the solutions. Don't see the solution immediately, destroys the learning process. There's no point in it unless you're in a rush. If you're in a rush, then go ahead, sure. But yeah, if you have the time, don't what do you say, directly look at the solutions, look at the exercises and then do that. In this thing, you may make an exception because these examples are kind of trivial. But in later examples, when you have more complicated things like computer vision and stuff, you may want to actually sit for a while and think about implementation before you directly jump to the solution. So I was hoping to cover this. Unfortunately, I didn't. We will continue. I'm so sorry to delay the coding by another lecture. I'll try to up the speed a little more. So thank you for joining. what would you guys like? Would you guys like to finish the coding by next class, or do you guys want to wait for me to, do you say, like this exercises thing that I mentioned? Do you guys want to go ahead and code it, or do you guys want me to code it in front of you in the next class?
We can try coding on ourselves.
Yeah. Yeah, you can
Uh,
send the link. We'll try out and we'll answer.
What else? Okay, how much work are you guys willing to take on? Since I'm slow on pace, I'm seeing how much I can defer to you guys. So let's see. Tensors I've explained. Okay. So now everyone has hopefully has an idea about how tensors are. Let's see what are some easier sections inside this. Okay, so this is fine. This is easy. Okay, so I hope everyone can read the basic operations thing over here. Let's see if I can finish it in like 5-10 minutes. Okay, so tensor addition over here is just going to, it's just going to add 10 to every value of the tensor. So you have tensor 1, 2, 3. You're going to chuck 10 extra to each of these entries. Multiplied by 10, same thing, multiply each of these things by 10. And one small thing that they mentioned in the notebook is like, okay, you see that you multiplied this by 10, but then actually, what do you say, stored the thing as like, 10, 20, 30, or 11, 12, 13. Instead, it retains the actual value. That's just something you guys probably know. Over here, torsion multiplication and torsion add is the same thing, just slightly more complicated, I suppose, for people who like it the hard way, I guess. And yeah, you can print it normally. Everything's exactly the same. Tensor multiplication is one thing that's sort of important, but it's trivially implemented in PyTorch. So all you'll have to do is you'll have to take, what do you say, torch.matmul over here. So matmul stands for matrix multiplication. You chuck in one tensor, you chuck in another tensor, and then you wrap it all in a torch.matmul matrix multiplication function, and it'll chuck out your, like, the tensor that you get as a result. So matmul, let's see if there's a better example of matmul. Okay, another thing. Oh, sure. Maybe I can cover this before I leave you guys. So I suppose, is everyone okay with 5 extra minutes? Okay, cool. I'll try to
Yeah, yeah.
cover until reshaping, stacking, and squeezing for everyone, and then I'll leave you guys to read the rest of this. So this section I want you guys to read just to understand how you can take NumPy data frames, which is their version of arrays, and tensors, and like, how you can interchange between these two things and convert one to the other. Reproducibility is just a note on how the random function works. And GPU's thing is a nice thing to understand about, like, how different, like I talked about CODA, right? And I briefly mentioned bend. So this thing is going to be a nice little exposition about understanding how, like, you can move your calculations to GPU and so forth. But ultimately, it's not that necessary if you want just a conceptual understanding of things. So this is optional. These two try to read on your own, and maybe this as well, but yeah, this is small anyway. I will try to cover until here. So let's see. Yeah, matrix multiplication, you chuck in matmul and you get everything. Fine. Okay, so min, max, sum, and all these aggregation functions. Aggregation just means collecting all your different values and putting out a single value. One important thing that I wanted to highlight, which would have been relevant if I got time to do PyGeometric, is that you'll notice that, like, if I suppose I have three values A, B, and C. Okay, A, B, and C. If I take the minimum of these three values, then it's going to be like 0, right? If I change the order of A, B, and C and I take the minimum again, it doesn't change the order, it doesn't change the resultant value at all. So this one little note that I wanted to point out is that all four of these functions are order invariant. It does not matter in which order you apply this operation, it will give you the same answer. And this is important when it comes to graph neural networks, which I would have shown prior. So this is all that there is to aggregation functions. All you'll have is you'll have your what do you say, your tensor over here, and then you'll just do dot min, dot max, dot mean, and so on. One thing to watch out about dot mean is you want to make sure that the data type is in float 32. So in what do you say? What was the thing where you convert one type to another? Case something. Can someone remind me, please? When we were changing data types from something like a float to an int or a float to a double. Typecasting, I think. Is that what it's called? Yeah, cool. So
Yeah,
this
yeah.
is your way of
Mm.
typecasting, where you take your tensor, you dot type, you put in the what do you say, data type you want. Make sure that you use the torch data type instead of the regular data types like int, float, and so on. So in this case, you'll have torch int 8, so 8 bits. You'll have torch float 32 for float 32 bits. And then after you convert this entire thing to a float 32 tensor, then you apply the mean function, and then it's not going to perform any issues. We all understand why what do you say, mean would be like why mean would throw in error when you try to do what do you say, dot mean, because like mean has addition. You're taking the average of something, you have to divide it by the number of things. You divide something, you automatically have floating point numbers. So that's a small thing. And another thing, if you want to just find the actual values of what do you say, the index where your minimum and maximum variables are, you just put a arg over here and it'll give you the index value. So again, most of these things are very simple to implement and very easy to play around with as well. So over here you'll see this is another example of converting something to float 16. You had an original tensor which wasn't in type float 16, put in type a dot type, and then chuck in the data type that you want to convert it to, and your data type is now updated to this thing. Now this is the last thing I'm going to cover today. So what do you say, in like any ML thing, you've seen that we obsess quite a lot over like tensors, tensor multiplication, and this and that. So you'll naturally wonder, okay, if I care so much about matrix multiplication and all that stuff, then I need to be able to multiply two matrices together. So if I have such a situation where I have two matrices and I can't multiply them together, because of the dimension mismatch, then it's going to be quite problematic. Now, in large models where you have like such hundreds of layers, each layer is having hundreds of neurons, sitting and manually trying to check each one's dimensions and ensuring that everyone matches one correctly is both very tedious and also very prone to future errors. So the reason why I say tedious is obviously it's pretty hard to look at hundreds of layers and make sure that everything has the right dimensions. Another thing is that looking at what do you say, looking at that layer, suppose everything is put fine and dandy, all the dimensions match. If you wanted to make updates and you wanted to add a new layer, or you wanted to reshape a new layer, or like change something about the current layer, these changes, this experimentation is very hard to do if you're so sensitive to the number of dimensions. So it's better to instead what do you say, perform these useful tools that allow you to just what do you say, convert your tensor into whatever convenient size it is to make sure that you don't throw errors all the time. So torch.reshape is going to take a tensor. So you have some tensor over here. Let's see, where are the examples for this? Yeah, okay. Yeah, so you have some tensor x, and then what you're going to do is you're going to do tensor.reshape, and then you're going to put in the dimensions of what you want. So in this case, x was first defined as just a one-dimensional tensor. So you have the numbers all from 1 to 8, and then you want to convert it into a two-dimensional tensor. So now instead of just being a one-dimensional tensor containing 7 entries, you're going to have a two-dimensional tensor, okay, containing again 8 entries. So the next thing you can do is you can change the view. The view is going to basically give you the same data, but it's going to change the shape. So it's going to, like, rearrange your elements such that, suppose you have a tensor containing 12 elements. Okay, so what view is going to allow you to do is you can either represent your 12 element tensor as a 3 by 4 matrix, or you can represent the same 3 by 4 matrix or your 12 element tensor as a 6 into 2 matrix. So you can just refactor things, shuffle things around, and change the shape of your tensor. So that's what view is for. Tensor.stack is going to just concatenate all your tensors together. So suppose we're okay. So do you guys remember the way first example over there where we saw something? The first example we saw of a tensor. So over here we have all these tensors, right? We have this particular tensor which contains all these vectors, and now we just saw the mention of the concat or the stack function in tensor. So what stack is going to do is it's going to concatenate each of these vectors such that it forms one single vector, and now it's going to be a tensor containing a single vector. So it goes from 7 4 1. It's going to just be a single list of everything over here. Okay, so that is the third function that we were looking at among those four. Let me just, yeah. Fine. And last two things, these two are going to be pretty easy. Squeeze is going to just basically remove all your one-dimensional things. So we saw that there was all this, like, basically, like, random stuff that we were doing for basically no reason. We were like, okay, why would I bother having a one-dimensional vector just packaged as rank 2 tensor for no reason, right? This one dimension isn't doing anything to, like, it isn't doing anything useful at all. So this, although it feels like a vector, we are forced to treat it as a rank 2 tensor, which is kind of redundant and not very, like, happy to deal with. So all we're going to do is we're going to take something redundant like this. So, and then we're going to apply the squeeze function, and it's going to squeeze it down to this actual vector that it was meant to be. Similarly, unsqueeze is going to do the same thing opposite way. So it's going to increase it by 1. So squeeze and unsqueeze are inverses of the other. If you were squeezing something, you would start from this one and you would remove redundant brackets over here. So in this case, you have one extra redundant bracket, you're going to remove that using squeeze. Unsqueeze is the inverse. You're going to start from here, you're going to add an extra redundant bracket. So on the side over here, you'll get this redundant bracket instead. So squeeze and unsqueeze are easy to understand. And what is left? Permute. Permute is just going to, what do you say, change the shape by permuting the values of things. So for example, I think we talked about image dimensions twice in this article, right? So in the first case, in the very first case, when we were talking about RGB values and stuff and why it's 3D, we saw that, okay, in this thing, he said it's 3 into 224 by 224, right? And I think later somewhere, I don't remember exactly where. Let's see if I can find out where it is. I think it was in random images. Yeah. So over here, you'll see instead of 3 into 224 into 224, you got 224 into 3. So what happened? You're just changing the order of these, dimensions. So that is what permute can do. Okay. And so that brings you to the end of these actually useful functions. Most of the useful thing comes from here. So everything that you saw before are trivial things that weren't like, they didn't feel like such a big deal. But this is where you start to see some of the utility of tensors and PyTorch a little more. And that is basically the end of it. The rest of it you can read on your own. This part is optional, read it if you want. This part is like a footnote, basically. So that's it for today. I'm sorry for taking an extra half an hour. Let's see. Yeah, go through the exercises, try to solve them. If you're not getting the exercise, refer the solutions. I'll put both of these links. And for today, if you guys want, you can go through the tensor library in the PyTorch documentation. It's going to explain the same things, but the reason why I want you guys to look at the documentation, why I want you guys to look at this specific page, is so that you can revise the things that you already learned, while also getting familiar with reading documentations, the habit of reading documentations. Deep learning is a fortunate field. Like, there's loads of documentation everywhere, there's loads of videos everywhere, and there's no shortage of content explaining what deep learning does. However, when you come to more niche software, some lesser known libraries, you're going to find that it's even difficult to find actual documentation sometimes. I suffer finding documentation for half of these tools, and like some of these tools are extremely useful to me, but I have to discard them simply because they have what do you say, very bad documentation, and that makes it basically unusable. So if I were instead relying on watching YouTube videos, I would be cooked. I would never actually be able to watch anything. I would never be able to use the software things that I relied on. So I will send the links of everything along with instructions about what to do. You have to read one documentation for like a specific class. The next thing I want you to do is I want you to have open two notebooks in Colab. One notebook is the exercise for PyTorch, where you will go through the like different tensor applications and revise that. The next one is geometric, PyTorch geometric, where you will simply run the what do you say, you will run the graphic neural network. So that done, I think we can leave today. Thank you for joining.
Thank you.
Thank you.
Thank you.
All right.
Thank
Thanks,
you.
bro.
See you guys next Wednesday.
Thank you.
Bye.
Yeah, bye.
Yeah.